Hey everyone, and welcome to this explainer. I've got to tell you, I am absolutely thrilled to have you here today because we are looking at a mind-bending new astrophysical discovery that literally challenges our most fundamental understanding of the cosmos. Seriously, we are going to explore a phenomenon that could fundamentally rewrite the rules of gravity at the very edge of the universe.
Okay, let's dive into this. Could Albert Einstein actually be wrong? That is a massive question, right? It carries some serious historical weight. For over 100 years, Einstein's legacy has been practically untouchable. The sheer audacity of even questioning it is huge. But as our telescopes get better and our observations of the deep universe get sharper and sharper, we have to follow the data, even if that data points to a glitch in the greatest physics theory ever written.
Now hold on, don't panic. We aren't just throwing Einstein's life's work into the trash. I absolutely love this brilliant analogy from Robin Wen, the lead researcher on this project from the University of Waterloo. He says, think of it as being like a footnote to Einstein's theory. Once you reach a cosmic scale, terms and conditions apply. That is just such a great way to frame it. We're not erasing the rulebook. We are just, finally, discovering its outer boundaries.
Section 1. Einstein's greatest theory. A century of unbroken success.
So before we go breaking the universe, let's establish our baseline. General relativity defines gravity not just as some invisible pulling force, but as the actual physical curvature of space and time itself. And on local scales, this math is flawlessly perfect. Whether we're predicting the quirky, wobbly orbit of Mercury in our own solar system or capturing actual photographs of supermassive black holes, Einstein's equations just nail it. Every single time. Moving on to Section 2, a glitch in gravity. The limits of general relativity. Let's move to and see how this builds, narratively zooming out from our safe, familiar local galaxy and stretching our view to the very edge of the observable universe. Things start getting remarkably weird. Looking at the sub-horizon scales, these are our familiar local neighborhoods, solar systems, black holes, local galaxies. Gravity behaves completely normally here, and Einstein's math works without a hitch. But then, look at the super-horizon scales. Once we hit that massive cosmological horizon, where the universe is expanding so incredibly fast that distant galaxies are moving away from us at near-light speeds, the math just starts to break down. Scientists are hitting apparent, undeniable inconsistencies.
So the crucial point is this new concept proposed by researchers at Waterloo and the University of British Columbia. Stripping away all the dense physics jargon, they've proposed what they call the cosmic glitch. It's a mathematical model where gravity simply acts a bit differently on vast cosmological scales compared to the smaller, local scales we're so used to. It is the exact same theory of gravity, just operating with a slightly altered gravitational constant way out at the edge of the universe.
Section 3, the 1% difference, quantifying the anomaly.
So how big of a glitch are we actually talking about here? Well, just 1%. Gravity becomes roughly 1% weaker when we're dealing with distances spanning billions of light years. I know, it sounds absolutely tiny, right? Almost like a rounding error. But in the incredibly precise high-stakes world of cosmology, a 1% difference across billions of light years is absolutely massive. It completely rewrites how we balance the cosmic checkbook.
And this brilliantly illustrates how that 1% modification acts. Looking at the equation of state for this modified dark energy component, you can see how it dynamically transitions over time. It acts like a fluid component that smoothly changes its behavior, moving from the universe's early fiery radiation era right into its matter era. It essentially adapts depending on whatever the dominant energy budget of the universe happens to be at that specific time.
Section 4. Solving cosmic tensions. Fixing the math of the universe.
Now you might be wondering, why does this matter? Well, this tiny 1% reduction isn't just a random error. It is a vital, missing puzzle piece that actually solves some massive discrepancies in physics. Think of astrophysics right now as a sort of cosmic crime scene, filled with observational tensions. First, we have the Hubble tension. The measurements of how fast the universe is expanding just don't match up depending on if you look locally or at the distant cosmic microwave background. Second, the clustering tension. We've got conflicting measurements on the actual density of matter. And third, there's the helium abundance anomaly from the Big Bang nucleosynthesis. The standard model is really struggling right now because our local universe measurements just aren't matching up with the distant universe.
Now, what's really interesting about this slide is how adding a negative cosmic glitch parameter mathematically bridges the gap between these conflicting cosmic measurements. You can see the constraints in the Hubble parameter easing and the constraints in the clustering tension easing too. It elegantly, literally, fixes the math of the universe. If we follow this timeline, we can trace the logarithmic running of this cosmic glitch across the entire history of the cosmos. Notice how the glitch was actually massively stronger all the way back at the fiery Big Bang. And then, as we move through time, approaching the universe's ultimate expansion, what we call the de Sitter scale, the glitch gradually vanishes. It tells this incredible story of an evolving feature of gravity itself.
Section 5. Return of the Aether. Rewriting Space and Time.
Okay, let's zoom all the way out now to the mind-bending philosophical implications of a universe with glitchy gravity. Way back in the 19th century, scientists thought light traveled through a physical substance called the ether. Einstein famously did away with that, establishing that there is no preferred frame of reference in the universe. Everything is relative to the observer. But this new mathematical glitch suggests that on the largest cosmological scales, the universe might actually have a preferred reference frame after all. We might literally be bringing the ether back, but in a totally modern quantum way. No way, right?
So here are the big picture implications. A 1% footnote could fundamentally rewrite our understanding of reality. We are looking at a potential violation of Lorentz symmetry on massive cosmic scales. It could finally provide that long-sought bridge to quantum gravity, uniting the physics of the very large with the very small. And most incredibly, it forces us to completely reevaluate the Big Bang singularity itself. Time and space as we know them might have started under completely different gravitational rules. Which leaves us with this final, truly provocative question. If gravity's rules really do change at the edge of the universe, what does that mean for the true nature of the Big Bang? If the very fabric of reality was fundamentally different at the dawn of time, then everything we thought we knew is really just the beginning. I hope this explainer sparked your curiosity and gave you a clear visual roadmap to this absolutely incredible scientific breakthrough. Keep questioning, keep looking up, and I'll catch you next time.